Welcome to the critical dimension tutorial for the DoubleFox Correlative Measurements software. We start with a piece of structured wafer on which we want to perform some critical dimension measurements. You can see the piece of wafer mounted on a sample holder below the FE-SEM column, and the structures are approximately oriented horizontally. The first step will be a basic alignment of the sample using the crosses which mark the space in between the individual dies. After that, we will use this alignment to move to the area of interest, which lies in the upper right with respect to the crosses, and then relocate and measure these structures on different dies. Now we start with a basic sample setup. We give it some size, which is can be any size basically. Give it some rectangle. Important is the die size. I've measured that before, and these are these values: 2.4 times 1.6 millimeter. And then we add a 0 position here, like that. We see a line grid now which matches the die dimensions. In the FE-SEM image, I choose the upper left corner of the cross for the alignment, which is easier than taking the center of the cross. When using the center point feature in SmartSEM, it is important to switch to stage-only movements, otherwise the beam shift may add unwanted offsets to the alignment. CorrMeas is not only using the XY position of the alignment, but also the current focal position. So it is important to care about this as well. Yes, this looks okay. Let's leave it like that. Now we use our 0 position and add it to the reference point list and correlate with the current stage position. I would like to be absolutely sure that we are really at the edge here. Yeah, that's the case. And now let's move further inside. That's the first cross, second, the third, fourth, fifth, sixth, seventh, and eighth. That should be the last one. And yeah, this is really the end here. Let's go to the same position as on the cross as on the first alignment, and make a good image to store the correct focal position. Yeah. Now we need to create a pattern, a grid of points, which corresponds to the die distance. And I've counted that these are 8 times 6 crosses we will use for our example, and we have to just change the minus sign there to move the points to the right direction. And then let's mark the current point and add it to the reference point list. And now we have 2 points added, and we should already be able to now align with these points and work with them. The best alignment is reached when we have 3 reference points. So we will now add the third reference point by going here into the corner. You can see the live image of the FE-SEM in CorrMeas overlaid with the position grid, and the alignment will be done in the original SmartSEM window. Let's make a good image. That's enough. Okay, we tell the system now that this point should be where the stage is currently, and add this as a third reference point. And now we have completely aligned everything. We can now check whether the alignment works correctly by going to one of the other points and just double clicking on one of the other points, and then Zooming in, and we can see that we have a mismatch here of about, what is that, 4 micrometer. The stage which is used in the system currently has a precision of about 5 micrometer. So that is the best we can get here. Because the system knows the die distance, we can now move from die to check the deviation of the alignment and the real positions. We anyway do the critical dimension measurement with some pattern matching and fine positioning, so the very exact positioning is not so important. You can use this grid already for automatic imaging. Here as an example, just highlighting these 4 points and then selecting grab positions recipe, pressing start, and the system automatically records images with the current magnification and stores them at the corresponding positions. You can nicely see the backlash operation of the stage going to each position, moving a little bit to the lower left corner and then back again to reach maximum position with this stage. Now you can see we have some images here in the table. You can double click on each of them and show it. And you can also right click and press center image, and then the wafer view or the sample view moves automatically to the location of that image. Now let's do what we actually wanted to do the automatic alignment. We start by going to the first point, our 0 position. Let's switch to the other side, and what we actually want to do is to image some of the finer structures there in the upper right, and going there now, zooming in to some extent. There it comes a little brighter, and now you see the bar here between these 2 wider tracks. And yeah, the target is now to measure the line width of this bar on the different dies. We start with aligning this exactly in the center. We need to have here our area of interest perfectly in the middle. In the CorrMeas, you see now we are a little bit aside the 0 position. We create a new position now at this point, and you see the relative indexing is still die 0, but some other coordinates. And in order to process all the positions, we create another grid parallel to the other one, and now we have also all our area of interests marked. Let's check a little bit how well we position. You can see we are not exactly there. It's about 2 micrometer or 3 micrometer offset. To do an automatic image analysis, the better the positioning works, the better the results. So we want to actually position perfectly. Therefore, we now use pattern matching to improve the positioning after the stage has moved to each individual position. For the automatic image evaluation, we should also consider using the right detector, and therefore we go to the SE detector, which makes in this case a better image, kind of shadow image. We use the state system to record the imaging conditions. The state system is a system to store different parameters of the system. And here, this status with the SE detector and this magnification we call now acquisition state. By pressing record, you can give it a name and then storing the imaging conditions. Now we want to create a reference image, and this should be taken from a low magnification. Also the in-lens detector looks here much better because it generates more contrast. We need to be sure that everything is centered correctly, and then we use the imaging state to give it a new state name, and we call it ref image. We can try this now by double clicking on the stored state once it goes to the acquisition, and now double clicking on the reference image switches it in magnification and detector to the overview condition. For storing the reference image, now we use a state called ref reduced, and this is used together with a ref image imaging condition. And when you press record, it and give it a name, and it stores the current image, which is recorded with the current view, and stores it to the reference database and automatically corrects the position using beam shift when the state is activated. And we can move a little bit to the side now and then press activate, and now the image is moved back to the original position. You can see this now. Yeah, it works from both sides, and we can also try it now by going to other positions and to check whether it works good. Maybe this is not a very good location. This yeah. Let's take the next one. Yeah, image taken and image is corrected. So works also here, and we are exactly in the center. Now we want to automate this. Let's go back to the 0 position and check that everything is okay. We are approximately there within the 2 micrometer or so. Yeah, we should create a script now, and we use a very simple one as the basis of this. You can select scripts down there from the recipes, right click, and then open the editor window. And this is one of the simplest scripts, which just moves to a position and grabs an image. And we can now edit this in the so-called automator. The automator has the advantage it can display this as text, and it can also display this in a visual representation. And what we want to do is now change the fact that it should not only just take an image, but also switch to the after the movement to the correct imaging conditions, then correct the positions, and then grab the image. So we need to put some functions in between the grabbing and the movement. So first we want to grab this reference position image, or correct the positioning by activating the state, and we can just drop the states into this sequence, and then it gets activated. So we first go to the referencing imaging conditions, and then we activate the acquisition script. And we give this recipe now a new name, and then it gets added to the list of recipes. And now we have it there and can choose it. Let us now select only the relevant points, and then add them to the process list and select our new grabbing script. And then we just need to press start to run the automatic process. And now it starts taking the reference image. And now the area of interest, and you can see we are absolutely in the center. It goes to the next position, takes the reference image, adjusts the position, and zooms in. And you can see how exactly the bars are at the center position, much less movement than the 5 micrometer precision the stage has. We still have some slight jittering in the position. This comes because depending on the calibration of the beam shift and the image magnification and so on. But in the worst case, one could add another refining step. But for our experiment here with the line width measurement, this precision should be good enough. You can see that this works even though the sample is relatively dirty. And in real life, one should of course work with as clean as possible samples, but showing this with a dirty sample indicates how robust this is. Yeah, and now we can look at the acquired images here, and yeah, we are exactly in the center. CorrMeas has also the possibility to filter the points, and we use this here now by creating a filter that only shows the selected positions. So that's a very easy filter, and a filter is a small program that evaluates an expression. And let's give it a name here, and then a small filter. Visible is selected means that if you execute that, then only the selected points stay visible, and we use this here now to see only our relevant points. As a next step, we want to evaluate the image and measure the line width, and we start by taking one of these images and putting it to the reference database, and we can then use the image filter designer to call up this image and then work with applying filters to this image. This is now a crop filter where we take only the middle part of the image and ignore the rest. And then the easiest thing is an average filter, which just averages all lines from top to bottom. And we just need to choose now the right position evaluation or profile evaluation, and now it automatically measures the width between a rising up and a falling down edge and shows directly the result of, in this case, 2.03 micrometer. And we can copy this image filter designer is creating automator code, and you can copy that directly in the automator window. And yeah, we use as a starting point again the grabbing script, and every time it goes to the this grabbing script iterates over positions, we use this and then delete what it is commonly doing, the whole sequence. Now it only iterates over positions, and we copy now the image evaluation sequence into this remaining placeholder there. It has restored the old sequence because it's not stored. Okay, let's delete it again and put it into this placeholder. Now for the copied code, the source image is still coming from the reference database. We need now to change this to take the currently evaluated image, and in the loop there's a variable e that counts from I that counts from 0 to the number of images, and we use then the function image read from selected image using the variable e as the index, and the image number 0 corresponds to the first image assigned to this line. So we take the first image of that line and load that. Now the result of this function need to be put into another variable which holds then the handle of that image, and we use the assignment operator to put this into the variable image, or IMG, yeah, which is used then in the crop function following this. The evaluation continues as shown, and we get as a result this width here, and this width value should now be written into the an additional column for each image. Yeah, and yeah, here it should, so that we have for each image the calculated width, and there's a function in the CorrMeas tab that adds a field to the table, and this function is called table table set selected field, and that function is here. And now we need just to use the index is the same variable we use for reading the image. That's the I. We can copy this here. Oh, yeah, like that, and putting it into the index. The field name we can choose. This should be not a sequence. No, it should be a constant value, and we call it width, meaning the width of this bar. And then the value has been calculated above. That's this variable there, and we can just place it there. Okay, that should be it. Yeah, we can run this now. Let's close the windows we don't need. And to run this over all images, we need to select all of them, put that to the recipe list, and we should maybe create a new recipe called evaluate. And we could also press run in this dialog, but it's normally much better to do it like that. And now it runs the evaluation for all the images, and we can see in the profile how it is shifting around. That's more or less the misalignment of each image. And there's a new column in the table called width, and there's a value for our image. Now we sort after width by clicking on the column header, and we can see that the smallest one is up there in the upper right corner. And now let's look where the largest one is. That's somewhere in the middle. It's probably because of this dirt that is sticking there too. Let's take another one. Yeah, this looks better now. And we can now compare our automatically measured values with a manual measured one. This shows here now 1 point. Okay, one have a little bit of freedom, of course, when you do it manually. It's 2.049 for the automatic one, and 2.00 for the manual one, but you can easily also put it to 0.3. So yeah, and then let's go to the bar which is smaller, and make an evaluation here as well. Yeah, here it shows 1.91 micrometer. So this is definitely smaller than the other one, and you can see we have a precision of at least something like 10 nanometer in determining the width of these bars. One can optimize this, of course, by taking a different amount of pixels in the image, but I think this is a relevant value, and because the evaluation is done in an automated way, you have a much higher reliability or comparability than if doing this by hand. Now a few words to the state system. The state system is very flexible and nothing is predefined. Each state consists of a recorder script and an activator script. And the idea is here to provide a flexible way of recording and replaying a set of parameters. In this case here, these are not only parameters, but also the reference imaging in combination with beam shift operation and so on. So the recorder script and the activator script, they are activated when you press record to record a new state, and then when you play back with the activate button. And this was a quite complex script. A very easy one, for example, is this image. This just records the variables brightness, contrast, detector, and magnification, and replays them when you activate this state again. Yeah. This recalling the states is easily integrated in the automation script. You just activate a state by a drag and drop, and you can basically also store a state if you want to create a state or record a state in an automated way. Both is possible and allows kind of teaching of the system. For example, going to different position, recording a state, and then playing back in a sequence is very easy, just done by interactive means and drag and drop. You can also load and store all the states into a file for backup, or if you get some nice recipes from someone else, you can load them in and use them in your own CorrMeas installation. And that is the same basically for all the scripts here. You can also here in the process list store and load the states, and also the stage move scripts and the grabbing scripts also all behaves the same way. You can edit all of them, and the idea behind that is that all these scripts then can be adapted to the different microscopes types with all with their special behavior. Now a few words about image alignment. You can, instead of working with a white background, you can load images and align them to use them for navigation. You can also load GDS files. In this case, we use a photo of this sample and load this in and align it on the background. And I want to show this here shortly. Here, this is a photo. You can give it an initial size, which is, if you don't use it, by the alignment, it's anyway rescaled the size of this of the photo. So we start with something. This is the same area we have been working before, and I counted the number of points, and we now need to tell the system which point belongs where. With 3 alignment points, the sample is aligned. So we take the first one, place it here. You can either use the stored positions for alignment, or you can move the stage there and then align to the stage position. We here just use the reference points, the stored points, and select the areas in the image which should correspond to these points. And now as soon as you have 3 points selected, the image jumps to the right position. We can use it now for navigation using the SEM. Let's switch to the SEM image, and then we can activate the live view to check how good the alignment is. For example, by going to the physical corner of the sample, and you can see the overlap between the photo and the live image. And this looks relatively good. Now, of course, in a photo, you can't zoom in so much without it getting pixelized. If you, for example, align to a GDS file, which is also possible, then you can zoom in further and further, and you get more and more details. You can now here, on top of this overlaid image, you can, of course, also store your images and use it for interactive work.